Thanks, Amanda. Now, hey, listen. During the break, did you talk to your daughter? Did you talk to your daughter and tell her you loved her? I did.
I did promise you, so anyway. Hopefully you've been staying with me all this time. This is the last topic as far as these videos are concerned. That's probably a good thing. Anyway, this is section 3.8. It's the Poisson distribution. My little bit of math history here. It's named after the famous French mathematician Poisson. And if you know your French, then you know that poisson is the French word for fish. So this is the famous French mathematician Simon Fish. Sounds better in French. Anyway. As far as the Poisson distribution is concerned, the basic idea of this is that we're working with, for the most part, time or spatial intervals. Doesn't have to be that way, and you'll see some examples where they aren't, but these are the most common types of examples. And the way that we work with this, let's go with the notion of time here, is that we're going to split a time period into many small intervals. And these small intervals are actually really small. The notion here is that within each interval, something occurs once or not at all. This could be something like accidents on a highway. This could be arrivals in a line, be it at a bank, at a grocery store, cars pulling up to an intersection, up to a stoplight, things being sent. Let's say we're talking about a stock firm and they're doing trades, so you might be doing your own online trades, and all of these people are making different online requests to make trades, and so the time intervals are so small that within each time interval, either one customer decides to make a trade and submits that request, or nobody does within that time interval. So the way that we work this here is the probability of one occurrence in the subinterval is going to be equal to lowercase p, and the probability of no occurrences is going to be 1 minus p. Well, from what we did in the hypergeometric, you may start thinking that there's a relationship here to the binomial or the geometric, and you would be right. It actually is a relationship to the binomial. So, one other thing that we're working with here is independence of intervals, or of subintervals. Basically what that's saying is whether something happens in a certain subinterval doesn't impact the probability of something happening in another subinterval. So what we're looking for here, as far as p of x is concerned, x is the number of occurrences. the number of accidents, the number of trading requests sent, the number of customers that show up, all different types of examples here. And so we're going to model this as a binomial. So this is going to be n choose x, p to the x, times 1 minus p to the n minus x. Now I know in the other situations we've converted 1 minus p to q, but because of something we need to do here, we're going to leave this in 1 minus p form. Okay, so what I said earlier is that we're letting these intervals become very, very small. So basically what we're doing is we're going to let n go to infinity, and we're going to look at the behavior of this as n goes to infinity. Okay? In addition to this, we still have this probability that's important here. And if we let n get very, very large, then the notion would be that p is getting very, very small. But for our purposes, there is still a value to np, a finite value. So n's getting huge, p's getting really small, but their product is finite. And that product we're going to denote by a lowercase Greek lambda. And this is the rate of occurrence. So, if we start writing this out, we've got n factorial over x factorial, to put our limit in there, times n minus x factorial. And we've got p to the x, but over here we have n times p is equal to lambda, so that'll give us p is equal to lambda divided by n. I'm going to make that substitution. So we've got lambda over n raised to the x, and then we have 1 minus lambda over n raised to the n minus x. And you start looking at this going, well, what the heck can I do with this? Well, there are some things. First off, one thing we can do is we can do some canceling. We have n factorial here, we have n minus x factorial here. So essentially what we can do is we can cancel all of the terms from n minus x on down to 1. So this is the limit as n goes to infinity of n times n minus 1 times n minus 2 down to n minus x plus 1. We still have x factorial right there. And at this point, we still have lambda over n to the x, 1 minus lambda over n to the n minus x. Although you can pause it, I'll still give you a moment to finish writing it down so you don't have to, because there's still a few more lines to this. Wish I could be watching you writing it down. At least that way I'd know when to continue. Okay, hopefully I gave you enough time there. So, at least until we do the next line, I'll leave this last line right here. So, as far as this limit's concerned, just like we do with summations and a lot of other things, we can look for some things to pull outside of the limit. So anything that doesn't involve n. So as far as we're concerned, x factorial in the denominator here certainly doesn't involve n. And we can split lambda over n to the x up to, into lambda to the x divided by n to the x. So we can then pull lambda to the x divided by x factorial outside of the limit. Now, as far as the next piece is concerned, we canceled n minus x terms from this denominator. So there are exactly x terms left in this numerator. Over here, we still have n to the x in the denominator, so we've got x n's. We have x terms up here. So for each one of these terms in this product, there's an n down here to divide it by. So this becomes n divided by n times n minus 1 divided by n times n minus 2 divided by n, all the way through n minus x plus 1 divided by n. We still have 1 minus lambda over n to the n minus x here. We're still going to have some stuff to do with that. Okay. So, as far as all of these are concerned, within this piece, remember we talked about the rational functions that we did with regard to looking at the limiting behavior of the hypergeometric. These are all rational functions in terms of n. They're all numerators and denominators are degree 1 polynomials in n, and the leading coefficients are all 1. So when we take the limit of each one of these, all of these are going to go to 1. So effectively at this point we've got lambda to the x over x factorial times the limit as n goes to infinity of 1 minus lambda over n to the n minus x. We're almost there. Oops. So as far as this is concerned, again, we're just carrying down this first term. One remaining thing we're going to do here is we're going to split this up. So this is going to be the limit as n goes to infinity of 1 minus lambda divided by n to the n times 1 minus lambda over n to the negative x. Now again, x is finite, n is going to infinity. Since n is going to infinity, lambda over n is going to 0, and hence this term right here, just like all of these terms up here, is going to 1. But as far as this is concerned, while lambda divided by n is going to 0, n is going to infinity. And if you remember from back in pre-calc and calculus, this is your definition of the exponential function. So this limit right here is e to the negative lambda. And so what we end up with is p of x equals lambda to the x, e to the negative lambda, divided by x factorial. And since we're letting n go to infinity, x is 0, 1, 2, 3, and so on. So our big limit that we started out with reduced to this. Put that back up at the top so you can see it as we're working through some examples. Okay, so we have p of x equals lambda to the x, e to the negative lambda divided by x factorial, x is 0, 1, 2, so on. Okay, so for our first example here, we're going to look at problem 127. This is page 136, and it says the following. The number of typing errors made by a typist has a Poisson distribution with an average of 4 errors per page. So that's our rate. Lambda is 4 errors per page. It says if more than 4 errors appear on a given page, the typist must retype the whole page. What is the probability that a randomly selected page does not need to be retyped? So if it doesn't need to be retyped, that means the number of errors has to be less than or equal to 4. So this one is going to be the sum, x equals 0 to 4, of 4 to the x. The 4 here corresponds to this 4, times e to the negative 4. Again, this 4 is coming from the same place, divided by x factorial. Now, as far as your calculator is concerned, just like we had the binomial PDF and CDF, we also have Poisson PDF and Poisson CDF functions. They're in the same menu as the binomial. PDF and CDF are located. Okay. And just like in the case of the binomial, the PDF is really the mass function. So this is what you're going to do for the equal to case, and the CDF is going to be for handling an interval like we have here. So for those of you with the TI-89, like I said, you're getting your dialog box for this. So when you plug in the Poisson CDF, you're going to put in, and this is for the 89, you're going to put in lambda is equal to 4, your lower value is 0, and your upper value is 4. Those of you with an 83 or an 84, when you're using this, the CDF on the 83 and 84, just like with the binomial, it's strictly a less than or equal to, which is good in this case because that's what we're working with. So what you're going to have is Poisson CDF, and you enter first the value of lambda and then the value of x in the less than or equal to case. So for this situation, you would enter 4, 4. If we were looking for the probability of 6 or fewer errors on a page, it would be 4, 6. And for those of you with the 89, it would be 0 and 6. When you plug that into your calculator, what you end up getting is 0.628837. So basically what that's telling you is if this were a real person, then approximately 37% of the pages that are typed would have to be retyped because about 37% of them have more than 4 errors. The next problem is number 128, following problem on this one. And 128 says the following. Cars arrive at a toll booth according to a Poisson process with mean 80 cars per hour. And then it says that if the attendant makes a 1-minute phone call, what is the probability that at least one car arrives during the call? So we're looking at the probability that x is greater than or equal to 1. Now, if you guys were actually in front of me instead of the camera, At this point, I would be asking you, do you think we should be using 80 in this problem? And hopefully, at this point, you're thinking, well, probably not. Because remember that for the purpose of this, we're looking at a 1-minute interval. Lambda, the rate is stated in terms of hours. So what we have to do is we have to convert this to a rate per minute. So as far as lambda is concerned for this problem, we have to take our 80 cars per hour and divide it by 60 minutes per hour so that lambda becomes 4/3 cars per minute. And that's what we'll be using in this problem. If your units for your rate lambda are not the same as the one, or the time interval or whatever you're working with is different than the event you're trying to find the probability of, you have to put them on the same scale. Now, as far as this is concerned, we can go ahead and use the calculator. We can use the CDF function, but there are a couple of things to note here. First off, we're looking for the probability that x is greater than or equal to 1. That's the same thing as 1 minus the probability that x equals 0, since that's the only other possibility. So this is 1 minus the 1 minus 4/3 to the x, but x is 0, times e to the negative lambda, so that's e to the negative 4/3 divided by 0 factorial, and this just becomes 1 minus e to the negative 4/3, which works out to be 0.7364. You could use the PDF function, the poisson PDF, to go ahead and get this. Again, for those of you with the 83s and 84s, it's still lambda and x. It's just the equal to case. For those of you with the 89s, you'd have to enter lambda and x. The big warning here for those of you with the 89s is that if you tried to do the x greater than or equal to 1 with the CDF function, and you put your lower value as 1 and your upper value as infinity, you're going to get an error statement from the 89 because it can't handle that summation. So for any scenario with the 89 where you're doing a greater than or equal to case with no upper limit, you have to do it as 1 minus the probability of being less than or equal to 1 below. So again, if just, let's say we were looking for the probability. Even when I'm on video camera, they die on me. So if you were looking for the probability that x is greater than or equal to 3, for the purpose of using the calculator, you would have to get the probability that x is less than or equal to 2, and then end up subtracting that from 1. One more of these problems here. This one was a time example. In this next case, we're looking at one that's commonly used in epidemiology, where we study health states and health conditions. This one right here is problem 136 on page 137. And it says the following. Increased research and discussion have focused on the number of illnesses involving the organism, I could never pronounce it, so I'll just say E. coli, which causes a breakdown of red blood cells and intestinal hemorrhages in its victims. Hope you're not eating. Anyway, sporadic outbreaks of E. coli have occurred in Colorado at a rate of approximately 2.4 per 100,000 for a period of 2 years. So 2.4 per 100,000 people per 2 years. So in Part A, it says if this rate has not changed and if 100,000 cases from Colorado are reviewed for this year, what is the probability that at least 5 cases of E. coli will be observed? Well, in case you don't have your book with you, let me reread this again. If this rate has not changed and if 100,000 cases from Colorado are reviewed for this year, what is the probability that at least 5 cases of E. coli will be observed? Well, the thing to note here is that this rate is given to us out of every 100,000 cases per 2 years. This problem in Part A is asking us to look at this in terms of a 1-year period. So as far as Part A is concerned, instead of using lambda equals 2.4, we're going to use lambda equals 1.2. And we want the probability that x is greater than or equal to 5. So this is the sum, x equals 5 to infinity of 1.2 to the x, e to the negative 1.2 divided by x factorial. We'll use the calculator and get 1 minus the probability that x is less than or equal to 4. The complement of 5 or more cases is 4 or fewer. So we're going to use Poisson CDF function. Lambda is 1.2. X is 4. This will give you 0.99225. So the probability that we want is 1 minus that, and that's going to be equal to 0.00775. As far as Part B is concerned, it says if 100,000 cases from Colorado are reviewed for this year and the mean number of E. coli cases exceeded 5, would you suspect that the state's mean E. coli rate has changed? Okay. Well, what this is saying right here is the probability of seeing 5 or more cases when the rate is 1.2 cases per 100,000 people in a single year. It's this number right here. So basically what this is saying is that we only expect to see this happen if we think about this as 0.008. We think about this happening basically 8 years out of every 1,000 years, or once in every 125 years. Does that mean it can happen without the rate increasing? Sure it does. Okay? But since it's only going to happen on average once out of every 125 years, then the general suspicion is going to be it probably didn't happen due to chance. And so somebody might be expecting or taking a look to see if there's something that caused that E. coli contamination rate to go up. On the other hand, if this probability had worked out to be something, say, like 0.2, then this would happen